Question 14, section 12.2. Set up the iterated integrals for both orders of integration, then evaluate the double integral using the easier order and explain why it's easier. We're doing the double integral of y squared e to the xy dA over the region D. D is bounded by y equals x, y equals 4, and x equals 0. Let's sketch the region. And sometimes sketching the region can give you some insight on things, not always. Okay, something's not going away on my side of things. There it goes. Okay. Y equals x, that's just a nice little diagonal line that bisects quadrant 1. Y equals 4 is the horizontal line through 4. And x equals 0, of course, is the y-axis. So we have this triangle. All right. Let's set up the dx integral first. In other words, let's set up what it would look like if we were going to do dx followed by dy. Y squared e to the xy. All right, if we're going to set it up dx first, then we need to know what x equals on the bottom, what x equals on the left and what x equals on the right. On the left side of the region, x is equal to 0. And on the right side of the region, x is equal to y. So we would be going from 0 to y. And then, followed by dy, we would need to know the constants that y equals on the bottom and y equals on the top. On the bottom, y is equal to 0, and of course on the top, y is equal to 4. So there's the integration if we were to do the dx integral first. But we're being asked to compare this versus what would happen if we wanted to do the dy integral first. xy dy dx. And if we're going to do that, then we need to think about what y equals on the bottom versus y equals on the top as equations, not as constants, or rather I should say as functions, not as constants. Oops, didn't mean to get rid of the whole picture. So let's clear out this. There goes my x-axis. I keep getting rid of parts I don't want to get rid of. There we go. And how did that disappear? I'm way up here. Okay. But if we're going to do the dy integral first, then we need to know what y equals on the bottom and what y equals on the top as functions of x. On the bottom of this rectangle, we have, this thing is being so persnickety. On the bottom of the rectangle, we have y equals x. This is the bottom. And on the top, we have y equals 4, which is technically a function, just happens to be a constant function. So we would be going from y equals x on the bottom to y equals 4 on the top. And then in terms of constants, what x equals on the left and what x equals on the right. On the left side, x is equal to 0. And on the far right corner of the lamina, x is equal to whatever the intersection of those are, but it's the intersection of y equals x and y equals 4. Well, if y equals 4 and the x and the y are equal, then the x is equal to 4. So it'd be going from 0 to 4. Now, which one's going to be easier? Well, let's think about this. If we were to do the top one first, I'm going to get a highlighter set up here. If we were going to do the top one first, we're going to do the top one and do dx first. Hold on, there's a better way to do that. There we go. If we were to do that integral first, then we would need to integrate the e to the x and everything else around it is constant. Well, that's not too bad. Now, if we were to do the other one first, the dy, then the integrand is a product of functions of y. It's y squared times e to xy, which means we would have to integrate that product most likely using integration by parts. Although it's not impossible, if I have the choice between integration by parts to do a function of a product, an integral of a function of a product of two functions, try this again. The integral of the product of two functions of y, that would require integration by parts here, versus the dx integral first, which is just the e to the x rule. I think doing the e to the x rule is much easier. So we're going to do the top method first. So we'll have to integrate with respect to x from 4 to y. All right, let's get this ready to go. All right. Okay, we're going to do the integral from, what was it? 0 to y of y squared e to the xy dx. And we technically could do a u substitution. If you need to, that's what you do. You could say u equals xy, and du is equal to, we're doing derivatives with respect to x, so it's y dx. Then you could borrow one of these y's with the dx to make the du package, and the extra y would wind up in the front. And we're going from x equals 0 to x equals y. Funny looking 0 down there. Let's fix that. Why does this erase way away from where I am? You can't see it on my end, but I just erased that 0 and you saw some other stuff disappear. Okay. We are integrating. Okay, we pulled off one of the y's. And then we substituted 0 for xy. And then the other y along with the dx became the du. Keeping in mind that y is a constant here. Wait a second. I botched that up a little bit. Let's fix that. Okay, we pull off one of the y's. We have e to the u. And the other y from the y squared gets packaged with the dx to make the du. Okay. All right, so the antiderivative will be y e to the u, but u is just holding the place of xy, so we'll bring that back in. And we are going from x equals 0 to x equals y. All right, when we put in y for the x, we get y e to the y times y, which is y squared, minus, when we substitute 0 for the x, we get y times e to the 0, which is just y times 1, which is y. This won't be too difficult an integral to do because we can do a u substitution on the y e to the y squared. But there's the results of the inner integral. The outer integral, I believe, was from 0 to 4. We can go back and look. Yes, we're doing the top. So the outer integral was 0 to 4 of what we have, dy. Integral 0 to 4 of y e to the y squared minus y dy. I'm going to expedite this one a little bit. I will mention that on the first part of the integral, I would do the two halves of the subtraction problem separately. But on the first part of the integral, you could say u equals y squared, du equals 2y dy. So we're off by a factor of 2. So we'd pick up an extra factor of 1/2 upon integration. We would end up getting 1/2 e to the y squared. And then minus the integral of y is 1/2 y squared. And this is going from 0 to 4. All right, when we substitute 4 for the y, we get 1/2 e to the 16th minus 1/2 of 16, which is 8. Minus, and when we substitute 0 for the y, we get 1/2 e to the 0, so 1/2, minus 1/2 0 squared, which is 0. And so we end up getting 1/2. Let's move this to the next page. We end up getting 1/2 e to the 16th. And then we had minus 8 and minus 1/2. 8 is 16 halves, minus 1/2 is minus 17 halves. Or if you wanted to factor out a 1/2, e to the 16th minus 7. That's a funny looking answer. I've seen worse though. All right, assuming nothing went off the rails, that should be good for that one.